All right, so we're going to be going ahead and we're going to be looking at this problem. So we have a rope and it's wrapped around a solid cylinder drum, and it has a moment of inertia represented by 1/2 mr squared. The drum has a fixed frictionless axle. The mass of the drum is 125 kilograms and it has a radius of 50 centimeters. The other end of the rope is tied to a block that has mass that equals 10 kilograms. We want to know, what is the angular acceleration of the drum? What is the linear acceleration of the block? And what is the tension of the rope, assuming that the rope does not slip. So when we think about the notes that we've been looking at, we did look at a 2-mass system where we had 2 masses hanging on either end of the pulley. And so in this one, we only have a 1 pulley or a 1 mass connected to the pulley. So let's go ahead and first draw a picture of what this looks like just so we can visualize it. And when we're doing that, we also want to make sure that we are identifying the direction of the rotation or which way is positive. So we have a pulley. Connected to that pulley, we're going to go ahead and we're going to put a mass. It doesn't really matter what side you put this mass on, so that's not going to matter. And then let's go ahead and, assuming that this block is going to be moving down, which it will, we're going to go ahead and say that way is positive, which means that moving counterclockwise is also positive, which is kind of helpful that we keep that as positive because we are used to looking at a rotating object and saying that the counterclockwise direction is positive. So now that we know kind of what we're dealing with, we are going to go ahead and we are going to use our tools that we just talked about, our different steps. We're going to draw a free body diagram of the mass. We're going to draw a free body diagram of our pulley, and then we're going to go ahead and combine those two equations to solve for our acceleration. Now, a little bit different than how this problem has it written, we are going to go ahead and solve for our linear acceleration first, because that's what we've kind of been looking at in our notes, and then we'll go ahead and go back and solve for angular acceleration and then the tension. So first, let's go ahead and start off with our mass. So if I drew my free body diagram, I'm going to go ahead and label this M. It's accelerating downwards, which means that my force of gravity acting on the mass is going to be greater than the tension in the string. And because we don't have two sides of this, I could just call this T. If I were to go ahead and write my Newton's second law for this equation, I'm going to go ahead and say the sum of all the forces acting on the mass is going to be equal to Fg minus Ft. And of course, we know that the sum of all the forces is also equal to Ma. We're going to go ahead and we're going to break apart Fg, and we will go ahead and get Mg minus T is going to be equal to mass times acceleration. So this is one equation that we're going to go ahead and keep our eye on. This is going to help us because we're going to use this equation to substitute into our pulley. So let's go ahead and look at our pulley. So we'll go ahead and we'll draw our pulley. I'm going to go ahead and draw the force that is acting on that. Now again, what's pulling that and what's rotating the pulley is the tension from the string. So this is going to be our torque. And I'm going to go ahead and just put like a little T there so we know it's the torque due to the tension, that force of tension. So if we think about our equations for this, and again, we only have one torque, which is really nice. The sum of all the torques is really just going to be the torque of the tension on the rope. And again, that's going to be positive because we did denote that turning the pulley this way was positive. So that is causing a positive angular rotation. This is also equal to I alpha. Now what we're going to do is we're going to go ahead and break apart our torque, and we're going to plug in our moment of inertia for I, and we're also going to plug in our linear acceleration for our rotational. And so we need to remember that A equals R alpha. So if we're going to be plugging in something for alpha, we're going to go ahead and divide both sides by R. And so what we're going to plug in is, for alpha, we're going to plug in A over R. So what that's going to look like is we're going to have our force, and again, this is a force due to tension. And actually what we can do, let's not call that the force due to tension. Let's go ahead and just call it what it is, which is the tension, which is just a capital T. And that's going to be times the radius is going to be equal to 1/2 m r squared. And then we're going to go ahead and plug in A over R. Now, cleaning this up, this R right here is going to cancel out with one of these R's. We also have one R on each side, so those get to cancel out. So our final equation is that tension equals 1/2 MA. So as we can see now, we still have two unknowns in our equations, but what we can do is we can go ahead and we could substitute in this equation right here, and we're going to substitute it into here for T, because those are going to be the same tensions. And then what we can do is we can solve for our linear acceleration. So what is that going to look like? We're going to go ahead and we're going to put our mg, and again, that's coming from this equation right here, minus this equation over here for our rotational, so that tension, MA, and then that's also going to be subject to MA. And you know what? I just realized we do want to be specific, and we want to make sure that we remember that this is the mass of the pulley. So I'm going to go ahead and make sure to put a little P here, because we do want to be careful about making sure we differentiate between the two masses. Okay, now what we want to do is we want to go ahead and solve for acceleration. So that means we need to get this right here, which has acceleration in it. We want to get it to the other side. So we're going to get mg. And at the same time of moving it over, I'm going to go ahead and pull out my A, because the A is going to be in both expressions. And this is going to be plus 1/2 mp. So go ahead and divide, and we'll get the expression A equals mg divided by m plus 1/2 mp. So this is going to be my expression to solve for the linear velocity of the system. So let's go ahead and plug in what variables we have here now. So in our problem, we are told that the mass of the block is 10 kilograms. We know that the acceleration to gravity, we're just going to go ahead and use our nice even 10. And we're going to go ahead and we're going to divide that by, again, the mass of the block, which was 10 kilograms, plus 1/2 the mass of the pulley, which in this problem was a pretty heavy pulley. It was 125 kilograms. So what we end up getting here is that our linear acceleration is 1.38 meters per second squared. So now that I have that expression, so that is going to be my first answer, we're going to go ahead and we're going to solve for our rotational acceleration. So we're going to use that equation that we know that relates our acceleration to our rotational acceleration. So our translational acceleration is going to be equal to the radius times our rotational acceleration. Divide both sides by r. And we are going to have A divided by R equals alpha. And again, that's the exact same equation that we just used in the previous step. So now that we can have this, we have 1.38 meters per second squared. And we're going to divide that all by the radius, which we are told was 50 centimeters, which is 0.500 meters. This is going to give us 2.76, and again, this is rotational, so it's going to be radians per second squared. So there is that equation. Now, the very last portion of this problem is asking us to solve for tension. So going back up to our two equations that we have circled here, we have this one and this one. what we're going to do is we're going to choose one of those two equations, plug in our acceleration to solve for the tension. Now, looking at these two equations, to me, this one is just a little bit more straightforward to look at. So I'm going to go ahead and use the rotational one that I solved for instead of the translational. I just think it'll be a little bit more straightforward. So we're going to use tension equals 1/2 the mass of the pulley times the acceleration. So what that's going to look like is tension is equal to 1/2 the mass of the pulley times our acceleration. So tension is going to be equal to 1/2 the mass of the pulley, which again, that is 125 kilograms. And again, this is why you want to make sure that you label things so you know which one you're talking about. And this is A, not alpha, so we're going to plug in our 1.38 meters per second squared. What I end up getting for my tension is 86.25 newtons. So those are our different parts of this problem. It is important that you are able to look at these two things and combine them. This is going to be really helpful, especially when we're solving those AP physics problems that ask us to derive equations. Being able to manipulate these equations and seeing where you can plug them into each other is a super powerful and helpful tool in these types of problems. So, hope this was helpful. We'll go ahead and we'll move on to a more complicated one in the next video.